Welcome to day 2. We're talking about specific heat capacity, and that picture has nothing to do with what I'm talking about. So if we're specific heat, we're looking at the symbol capital C or capital C little p. It doesn't. Nobody really cares either one. So the specific heat is the amount of heat energy needed to raise the temperature of 1 gram of a sample of matter by 1 degree Celsius or 1 Kelvin. They have the same increment, so it doesn't really matter. So basically what's going to go on is if you have two matches right here, the same amount of heat added, well, water is going to take about 30 times longer to heat up than gold. You guys probably already knew that. That's because water is indeed very, very special. So now the quantity of energy transferred as heat during a temperature change depends on either the nature of the material, that's going to be the magic in the chemical bonds and that crazy stuff, the mass of the material, how much you have, and the size of the temperature change. So we have 3 different masses right here and 3 different materials, but they would all have different specific heats, but these would all, and it just kind of shows you how that would work. They would all absorb the same amount of heat though. So different materials will heat up at different rates though. So like something like gold and aluminum, which are both metals, if we still have one match here and one match here, I don't know how much heat that is, but it will take about, gold will heat up 7 times faster because it has a much lower specific heat than aluminum. Aluminum will heat up slower because it has a higher specific heat. All right. Now, just a fun fact, one match is actually about 4 kilojoules of heat. I kind of figured that out one time. So thermal insulators are things that have high specific heats. You know, something like on the space shuttle, the bottom of the space shuttle is coated with was coated with this silicone so that it could absorb quite an intense amount of heat. That's why that would protect the astronauts upon reentry, and it worked really, really, really well until the Space Shuttle Columbia was losing all of its tiles whenever it was launching. And they didn't know it, and so they tried to re-enter the atmosphere, and that is the tragedy of of what happened to the Space Shuttle Columbia. It just absolutely disintegrated when it was re-entering. So we had to approach that problem. That's probably part of the reason why we don't use the Space Shuttle anymore. Now they have a small amount of heat with a small temperature change, like this insulation here, and it heats up very, very slowly. So a good example is water. Water has one of the highest specific heats that we know of that's very common. So now a thermal conductor is mostly metal. That's the best example. It's something with a low heat capacity, and it heats up very, very quickly. Something like copper will heat up much faster than water, right? You notice your copper pot will heat up a lot faster than the water inside of it, right? Whenever you boil water. Well, this is why. It's because of their specific heats. So we will use this cool little equation. Now this is easy algebra here, where we call this Q equals MCAT, right? It looks like a cat. Q is the heat. Heat absorbed or lost, and its units are joules or kilojoules. For mass, the units need to be grams. It can do kilograms, but if you do kilograms, it's going to mess up your heat. So we'll just keep grams for now. Specific heat is going to be joules per grams degree Celsius. Remember, that was the amount of heat per 1 gram per 1 degree Celsius. Remember we talked about that in the previous slide. The change in temperature, delta means change. So the change in temperature is the final temperature minus the initial temperature, and the units are Celsius or Kelvin. Now, why does Mr. Russell always talk about cats? Does he have a cat obsession? Well, not really. It just works out that way. So we have a bunch of specific heats here that are listed. These are intensive properties that don't ever change. So the water, as you can see, is very, very high with 4.18, and lead is very, very low. Now notice that water as a solid, also known as ice, is a little bit lower, and we'll talk about why that is in a little bit later. So when we calculate these, they're very easy calculations where we have a 32 gram sample of copper was heated from 16 degrees Celsius to 61 degrees Celsius when it absorbed 554 joules of heat. We want to calculate the specific heat. So we have our known information here. We just glean all that down into one little problem, and we're looking for C. So I'm not really concerned with you being able to do the algebra here, but you would just input your values here and solve for C. And once you find that, you end up with 0.3866 joules per grams degree Celsius. For the example number 2, the specific heat of aluminum is 0.899 joules per grams degrees Celsius. If a 75.0 gram sample of aluminum is heated from 25 degrees Celsius to 40 degrees Celsius, how much heat did the sample of aluminum gain? So we'll still glean our information here. We have our specific heat, our mass, and our change in temperature, our final temperature minus our initial. That's usually the toughest part for students. Make sure you subtract the right ones. If it increased in temperature, it should be a positive value. If it decreased in temperature, then it will be a negative value, and that's allowed to happen. So you'll get Q equals MCAT, and you'll get that, multiply them all together, and you get your answer. Now, a good challenge question. What would be the temperature of a 24.2 gram sample of carbon if 575.6 joules of heat energy was applied to a sample originally at 25.0 degrees Celsius? If you're tired of me reading all these, why don't you just go ahead and skip them, or skip ahead, or you can use the YouTube function to increase the playback speed and make it go a little faster. So check it out. You have your known information here. Now we know everything except we kind of know half of our change in temperature. We know that we don't know the final temperature, but we do know the initial one, which is 25 degrees Celsius. So I'll still input it into here algebraically, and I have everything, and I'll just solve for TF. Now the problem is that this is, algebraically in a fraction, so I'm going to multiply these two and then move them over to the other side and get 33.5, and then I will get 58.55 degrees Celsius. Now a sample of water is raised at temperature from 45.7 degrees Celsius to 89.9 degrees Celsius when 4.36 kilojoules of heat energy was applied. What is the mass of the water sample? So if we glean our information again, the big hitch here is we had kilojoules right here, but our specific heat of water is in joules per grams degree Celsius. So we need to make sure that our units match up. So that's a trick that sometimes you see sometimes. I just want to make y'all aware. And then we have mass is our unknown, and we will put it all into our equation and then solve for mass, which is 23.6 grams of water. And now that seems to make sense. So who cares, right? Why would you want to know the specific heat? Well, you can identify a substance by its specific heat. Remember, those table of values are all known values, and they're locked away in a table somewhere. And also, this unlocks the door for understanding how many food calories there are. That's how we are able to understand why Cheetos have so many calories, right? Well, we actually just burn those Cheetos, and we can understand how much energy it takes to burn one of those Cheetos. Kind of cool, right? So now, why does water have such a high specific heat? Now, we talked about it has to do with the mass and also the change in temperature, but the specific heat also has to do with the nature. The nature of it is the bonding that's going on. Water has lots and lots of hydrogen bonds. We've talked about this one before. Now, ice has a few hydrogen bonds. Now, remember, they're locked into place. Now, water itself has this hydrogen bond here, but it can also break this and form another bond. So it has many more hydrogen bonds. The more bonding, or the more strength of the bonds, increases the specific heat. So the stronger the bonds, the stronger the intermolecular forces, the stronger the specific heat. Okay, so that's really the key there. All right, have a good day.